Here we take a look at mass spectrometry. This is just one of the topics in analytical chemistry. In the topic analytical chemistry, we analyze chemicals to see what's present. Together with mass spectrometry, in this topic analytical, we also study nuclear magnetic resonance spectroscopy, infrared spectroscopy, ultraviolet and visible spectroscopy, volumetric analysis and chromatography. So let's get on with mass spectrometry, or the mass spectrometer. A mass spectrometer looks something like this today. This is a modern mass spectrometer. You can see connected into a computer, which will show on the screen the graphical results, which can then be printed. Also, the benefit of linking the mass spectrometer or any spectrometer device to a computer is that the computer can have a database of data from literally thousands of different chemicals. And of course, once information is fed into the computer about the current sample, the computer can look into the database to see if it can recognize the data as something that it already has in the data bank. And such a computer then could perhaps feed back information about what it would appear to be. I'd like to emphasize at this point that we are not using what is known as a time-of-flight mass spectrometer. Many modern mass spectrometers work on the principle of what is known as time-of-flight, distinguishing between different ions on the basis of how fast they travel a certain distance. Here, I'm going to show you three different pictures of different mass spectrometers. All will be based on separating positive ions on the basis of their mass and charge. Let's take a quick look at this one, and as I've said, we'll be looking at three separate diagrams, and we should get a little bit out of each. So number one, the first thing we've got to do is get the sample into the sample chamber. If it's a gas, then it can be straightforwardly put in, but if it's a liquid, it will have to be vaporized. If it's a solid, it will have to be melted and vaporized, and that will then require an oven, which can reach a very high temperature. So we end up with a vaporized sample in here. We then have an electron gun which will fire electrons at the vaporized molecules, knocking one electron off the molecule, and in some rarer cases it may knock 2 electrons off the molecules. It will also tend to fragment the molecule, in other words break the molecule up into smaller parts, and we'll see how by learning about fragmentation and learning to interpret fragmentation, we can elucidate to some extent the actual structure of the molecule. Next, we have an electric field, and the purpose of the electric field is to get the positive ions that have been created because the molecule has been struck by an electron, creating an M+ molecule plus 2 electrons. That's the electron that it was struck by, plus the electron that's come off the molecule. Now, sometimes that M+ ion will be struck by another electron and create an M++ plus 2E-. But this is going to be, these will be much more scarce, of course. This is known as the molecular ion. That's the molecule itself with an electron knocked off. It will have the same mass as the molecule itself, since the electron knocked off has negligible mass. Now, once we've formed these so-called molecular ions, and indeed some of the M++ ions and some fragments will have been created as well, all the positive ions will start streaming in this direction. Why? Because of the electric field. By having a positive and negative plate, it's possible to get the electrons, or these cations, streaming in one particular direction. There will be some kind of slit which will have the purpose, perhaps somewhere like this, of focusing this stream of positive ions into a narrow beam. And this narrow beam will then begin to enter this magnetic field. If the magnetic field was switched off, they would continue straight through. But in the presence of the magnetic field, these charged particles themselves have a degree of magnetism which causes them to be deflected It depends on the momentum they have. The more momentum they have, the less they'll be deflected. The less momentum they have, the more they will be deflected. So in effect, they're being deflected according to their mass to charge ratio. Let's look at each of these separately. Why should they be deflected according to their mass differently? Why should a heavier particle be deflected less than a lighter particle? Well, simply again on the basis of the momentum the particle has. Two particles moving at the same speed, one heavier than the other. It's like having someone very heavy bumping into you compared to someone very light bumping into you at the same speed. Clearly the heavier person has more momentum, and that's what's happening here with mass. The heavier particle coming in with more momentum ends up being deflected less than a particle traveling at the same speed but lighter. What about charge? How does it influence the whole thing? Well, this is to do with the electric field. If you have a 1+ ion versus a 2+ ion, and let us say that they are the same particle, they have the same mass, but one has twice the charge. With twice the charge, it's going to be influenced much more in the electric field, and that's going to accelerate it faster. So as a result, this particle here with the bigger charge is going to be traveling faster. So which particle is going to be deflected the most? Which particle is going to be deflected the least? I think you can see that the particle that is lightest and traveling the slowest, think of a particle that is the lightest one in there, and it's also traveling the slowest. In other words, it's going to have a positive charge rather than a 2+ charge. It's going to be deflected the most because traveling slowly and being relatively light, I should say it's traveling relatively slowly compared to other particles, traveling and being relatively light, it's going to be deflected the most. If we take the opposite to that, the heaviest particle, which is traveling the fastest because it's got a large charge, it's going to have the least deflection. And then we have lots in between. So this is why we say that the particles are separated according to their mass to charge ratio. And this then creates a beam. Now some of the positive ions, as they're deflected, end up hitting the sides of the tube. They get absorbed and they don't make it any further. But there will be particular ions which have just exactly the right mass to charge ratio at this particular setting of the magnetic field to focus right up here and hit the detector at the far end. What we can do then is change the strength of the magnetic field so that we bring different positive ions into this particular line here, and they hit the detector. So as the magnetic field, for example, would be increased, we would find that something that wasn't deflected enough, we increase the magnetic field, and we find now that it begins to get deflected a bit more, increase it a bit more, and eventually when you increase it just to the right amount, it's going to be deflected by the right amount to head straight up the tube and be detected at the far end. So if we tune, as it were, through the magnetic field, increasing the strength of the magnetic field, at a low magnetic field strength we're going to be focusing onto the detector the relatively light particles that are traveling relatively slowly, and by the time we get to the far end of the strength of the magnetic field, we'll be focusing then the heaviest particles that are traveling the fastest, in other words, those that have the most momentum. Let's take a look at another diagram of a mass spectrometer to see if we can pick up anything extra here. Well, what I like about this one is, and the reason I put it in, is because it helps us to show why these M+ ions, which would be located in here, let's say we get the M+ ions created in here, why did they start heading in this direction? Well, if we have a positive plate here and a negative plate here, they're going to be repelled by the positive plate and attracted towards the negative plate, which would explain why they start streaming in this direction. Now, what this is referring to here, the detector, there are different detectors. What a mass spectrometer really does is it really only separates the M+ ions, these positive ions. It separates them so that they come out at the far end at different times. And you need some detector here, which quite often is a flame ionization device. This is the same kind of thing actually that happens in gas chromatography. Gas chromatography doesn't tell you what you've got. What gas chromatography does is to separate the different components so that they emerge at the end at different times. So you need some kind of device, electronic device perhaps, to detect what's coming out at a particular time, at a particular mass to charge ratio. So that's what it's talking about here when it's referring to a spray. It's being sprayed into a flame and then the material is analyzed in this particular case. But different mass spectrometers will be set up with different detection devices. I also like the word electromagnetic. In a mass spectrometer, it's not a magnet that's doing the separation. It's not the electric field that's doing the separation. It's a combination of the electric and magnetic fields. So it's better to use the term electromagnetic. And here's a third and final image from a different source. And it's referring to acceleration plates. Again, the idea that we create in here the M+ ion. And if we should make this particular plate positive and this particular plate negative, we're going to get repulsion from the positive plate, and that's going to cause them streaming here. I also like the idea of the small slit in this accelerating plate, the negative plate, where it will focus the beam to produce a narrow beam, which you see here. And then we've got the magnetic field here. The magnetic field was switched off. The M+ ion would just go straight on through, but with the magnetic field switched on, it's going to be deflected. Something extra it gives here is that while we have the electron gun here, it's firing electrons in this direction, and the electrons don't just simply disappear. There is some material which absorbs the electrons at the bottom, the electrons that haven't struck anything or whatever. Indeed, we are aware that when the electrons strike a molecule, it actually creates a second electron. So there's an electron collecting device here. And again, this picks up on the theme I talked about. You notice here, at this particular strength of magnetic field, it refers to this beam representing the most massive ions. They have been deflected, I think you'll agree, the least. And the ones that have been deflected the most are these ones over here, represented by this beam. These are the least massive ions deflected the most. And then you've got your collecting screen. But this has to be connected to something which is able to detect and then graphically or whatever represent what was hitting the collecting screen at a particular point. A little more detail is brought out by this slide. First of all, let's look at the flow chart. We vaporize the molecules, so they're in a gas phase. That's our source. Then we've got essentially, I suppose, the analyzer is where we have the electromagnetic fields separating out the positive ions. Then we have the detector, and the detector has to be connected, as I said, to some kind of, the detector may be the flame ionization device, but the flame ionization device gives data that needs to be interpreted, so you have to have some data system to interpret it, which will then give a printout, typically a graph. You notice that this dashed area here shows that this all has to be in a vacuum, and here's the explanation why. The vacuum pump is needed in order to operate the instrument, as ions may have to travel over a meter in order to reach the ion detection system. And notably here, if the vacuum was not present, the ions would collide with gas molecules present in the instrument before reaching the detector, and that would obviously have an influence on them. So let's take a look then at some of these aspects in detail. There are four main stages then in the process. And I would emphasize you don't need to know the details of these, but I'm going to it's worth spending 20 minutes going through the basic operation of a mass spectrometer. Right, number one, ionization. The vaporized sample is put into the mass spectrometer. It has to be then ionized. So first, before this actually, if it's a solid or liquid, we have to get it vaporized. And so there will be an oven that's capable of reaching a very high temperature to vaporize any sample that might be put in. Having vaporized them, an electron, one or more electrons, are removed from the molecule, and that's done by an electron gun that strikes these molecules with electrons. And we saw how you get M plus struck by an electron, knocks an electron off, creating M plus, and therefore you've got 2E minus to balance this on the right. And here we see a diagram of the electron gun here, and then you have a device which collects and absorbs those electrons. Meanwhile, you have created in here your M plus ion, which will start streaming in this direction, away from the positive plate and towards the negative plate. The positively charged species then go into the accelerating chamber. If we go back to the previous slide, this presumably is what they're referring to as the accelerating chamber here. So that's the first stage. Second stage is acceleration. The ions are sent flying, basically. The ions are subjected to an electric field, as I've explained. You've got the positive plate and the negative plate. In fact, it's increasing in strength, this electric field, and that's going to get the M plus ion created in here, repelling away from this positive plate here and heading towards the single negative and the double negative, getting them streaming in this direction before they enter the magnetic field. Three is the deflection now. The heavy ions are deflected less than the lighter ions. Therefore, the ions are separated according to their atomic masses and travel to a different path through a different path in the mass spectrometer. I'm not too happy with placing the emphasis solely on being separated according to their masses, and it's important that we should use the idea of being separated according to their mass to charge ratio. I explained earlier that a particle with a bigger charge is influenced more by the electric field and is accelerated more. So in effect, it's both mass and charge that causes the positive ions of different masses and different charges to be separated. And four, the detection, detected and tallied. If you think of, in simple terms, that something comes in here and strikes this point, and when it does, it's tallied. Something goes down to tally it. The next one comes in, strikes, let's here, and it gets tallied. And as they come in, different points, they get tallied. So a second one comes in here, second one in here, one comes in here for the first time, one comes in here, another one comes in there, another one comes in here, another one comes in for the first time here, another one comes in there, another one comes in here for the first time, another one comes in here, another one comes in here now, another one comes in here, another one comes in here, another one comes in here, second comes in here, and we're literally getting a tally as they strike the detector. And this is what's going to create then these lines on the graph. And of course, the bigger the line, the bigger the tally. And we'll see how we use the heights of the lines, or peaks, or in the case of peaks, it should really be the area under the peak, how we compare those to work out the relative abundance of each of these positive ions hitting the detector. To make sure that all of the ions are detected, you have to vary the strength of the accelerating field. Well, again, you see here that different sources will describe it differently. I described how we took the magnetic field and we varied the strength of the magnetic field. When the magnetic field was weak, we were focusing in relatively light, relatively slow moving, in other words, relatively low charged, 1+ particles. And then we increased the strength of the magnetic field, and as we did so, then we started to focus in particles with a bigger mass to charge ratio. What one could do as an alternative, instead of keeping the electric field constant and varying the magnetic field, you could do it the other way around. You could keep the magnetic field constant and change the strength of the electric field, which is in effect changing the speed or acceleration of the positive ions. The detector records each species as a peak on the trace, on the basis of this tally that I've tried to present. What's the important principle? When the detector is struck by an ion, it injects secondary electrons, basically amplifying the ion current, where it is passed to a computer for processing, and a mass spectrum is produced. Not a physicist, but I get the idea that when a particle strikes here, it causes a secondary effect. It sends off an electron through a circuit which registers somewhere, and then this begins to build up, possibly using a photomultiplier, or whatever the term is, and then that gives us a readout. We've spent now just over 20 minutes looking at the design of a mass spectrometer, and I think that was not only worthwhile but necessary. I can't see how it would be good for a student just to get started in with interpreting spectra. Having said that, that first 20 minutes is not going to be tested in much detail. You should have a basic outline of those 4 stages we've just looked at. We're going to begin by taking a look at how mass spectrometry can be used to analyze the isotopes of an element and give us the relative atomic mass for any particular element. So we're going to start with boron. Boron is atomic number 5. Its relative atomic mass is 11. So in terms of the notation, it would be 11 over 5. But is it exactly 11? Let's look on to see. Here is the mass spectrum for boron. The numbers are missing here. This should record 10, and this should record 11. Now you'll notice that in terms of the heights of these 2 peaks, there's much more, this in terms of the tally, so to speak, that I described, much more tallied for the isotope of atomic mass 10. I could be wrong in terms of the relative atomic mass. I should have checked before I went on. It could be that it's 10 over 5. I'm not sure. You need to check that with the periodic table, which I don't have at the moment. But anyway, I'm just beginning, when I look at this and see that the lighter isotope is so much more abundant, it's leading me to conclude that the relative atomic mass would probably be presented as 10, not as 11. But let's go back to how we interpret this. If you were to take out a millimeter ruler, should this be on a page in front of you, and you measured the height of this particular line and did the same for this other line, and let us say, for the sake of simplicity, that this came out as 81 millimeters, and this came out as, again, for simplicity, 19 millimeters. You notice that the 2 sum up to 100 millimeters, 81 and 19. Now, if you look at what fraction this is of the total of the 2 heights, it's 19 out of 100, and that in fact gives us directly the relative abundance of the isotope of atomic mass 11, 19% abundant, and the other is 81% abundant, because it was 81 millimeters of a total length of the 2 of 100 millimeters, so it's 81%. This is done more precisely. Turns out 81.3% of relative atomic mass 10 and 18.7% of the other. Problem is, how would we work out the relative atomic mass, which is the average mass of the isotopes of the element, taking into consideration their relative abundance? I'll say that again, because that's important, and there are 2 aspects to that. The relative atomic mass is the average mass, what? Of the isotopes, taking into consideration what? The relative abundance. Now, if I was to take, in order to do that, what I could do is, if I was to take, and there's a simpler way of doing this as we'll see in a moment, or at least a simpler way of presenting, if I was to take 83%, which is, sorry, 81.3%, which is 81 over 100, to change from a percent to a fraction, you divide the percent by 100. If I was to take 81.3% of 10, that's what it represents, and I was to add that to 18%, which is 18.7 over 100, see this is two separate things here, of this atomic mass, 11. If I add those together, that will give me the relative atomic mass. Since both numbers are divided by 100, the common denominator is 100, so actually we could simply write that as 81.3 times 10 plus 18.7 times 11. And if you work that out, that will give you the relative atomic mass of this particular element, boron. And we'll arrive at that answer in a moment. Just going through a few slides here. Same slide again. So the results are plotted on a chart showing the percentage abundance of the isotopes. Percentage abundance 81.3, percentage abundance 18.7. Remember 10 and 11 here. If we assume that the charge on each ion is +1, then the mass to charge ratio is the same as the atomic mass of the ion. The mass spectrum above then is for boron. What it's saying there is, of course, had one of them been 2+, if you have your mass divided by your charge, now if the charge is 1, you're simply dividing the mass by 1. So in fact the mass to charge ratio is simply the mass, given that the charge is 1. But had it been a 2+ ion, then in fact what you're getting for that peak is half the actual mass, given that you're dividing the mass by the charge, which in this case would be 2. The number of peaks tells you how many isotopes there are. So 2 peaks, there are 2 isotopes of boron, at least present in this sample. The atomic mass of each is read from the x-axis, so 10 and 11. Here one of the isotopes is 10, the other is 11. The height of each peak tells you its percentage abundance. This means that out of 100 atoms, 81.7 atoms would be boron and 18.7, sorry, boron 10 and the other boron 11. Of course, you can't have 0.7 of an atom. So if we were to do it out of 1,000, if we analysed 1,000 atoms, what it's saying is there would be 817 of them would be boron 11, boron 10, sorry, and 187, can't be right, 81.7. This typing error here, this should have been copied through correctly as 81.3. So there'd be 813 of them would be boron 10, and there would be 187 of them would be boron 11. Hope that's clear enough. So to work out the average isotopic mass, you use the method I showed there. What you do, you can put them all over 100, since 100 is a common denominator here. And you would take 81.3, that's the percentage, times 10. And you'd add it to 18.7 times 11, and it seems that comes out to be 10.8, and that's the relative atomic mass according to the abundance of the isotopes in this particular sample. We'll look at the isotopes of bromine now. Bromine, of course, is a diatomic molecule, so you've got Br, Br, and we'll have to be careful about that. So here's a particular mass spectrum for it, And you'll notice that we've ended up here apparently with 5 different peaks. And there's none at 80, which is there, but there's one at 79, one at 81. And then we have some which are around about twice those values, 158, 160 and 162. We've also been given the natural abundances here. But let's see if we can establish what all of these peaks are from. Well, there are bromine atoms which have an atomic mass of 79. The only other type of bromine atom that's found naturally are those that have an atomic mass of 81. Now, if you have a bromine atom that's made up of 2 that have a mass of 79, this is the way to present it, this is the proper notation, then 2 79s will clearly give us the 158. How likely is that? Well, in terms of the 79, actually, these 2 isotopes are more or less equally abundant. There's ever so slightly more of the Br79. So the chances of that are about 50%. The chances of getting a Br79 about 50%. You'll have to be a little bit better at the statistical math to work out what the chances are of this, but we're not interested in that detail. You could also, in simple terms, have one that's made up of 79 and 80. Sorry, 81. But actually, it could have been the other way around, and statistically, you need to consider this possibility as a separate possibility, namely 81 with 79. And then you could also have bromine where they are both 81s. And you can see here that these both come out to be 160. This one comes out to be 162. And statistically, you can see why this one has the tallest of the peaks. But you're not likely to be examined on that in any detail. And 158 and 162, in terms of the fact that these are more or less equally abundant, shouldn't surprise us either, that those 2 peaks are about the same. The 162 peak is ever so slightly lower, which is in fitting with this lower percentage abundance. Okay, let's move on to the next one. Isotopes then within a compound. You know, even in simple terms, when you've got water, we always expect that it's going to be normal hydrogen. Normal hydrogen has got no neutrons, just 1 proton and 1 electron. So the atomic mass of normal hydrogen is 1. There's a tiny, tiny amount of deuterium and a very, very tiny amount of tritium. So there is a very, very tiny possibility that you could end up with water which doesn't have the normal hydrogen isotope, but has either deuterium or tritium instead. Equally with a hydrocarbon, like the simple one, methane, there's always the possibility there that you have got, instead of the normal carbon, carbon 12, that you maybe have carbon 14. Or some other isotope of carbon. So here we're going to analyze this, or take a look at some of the effects of this and how it shows up in mass spectrometry. Vinyl chloride is a molecule made up, looks like ethene, except one of the hydrogens has been replaced by a chlorine. Now, there are 2 isotopes of chlorine, Cl35 and Cl37. Now, the lighter isotope, around about 75% of that in nature, and only 25% of this, roughly speaking. So you're 3 times more likely to come across a Cl35 than a Cl37. And I think that's what's showing up here as well. We'll come to try and explain why we're getting these particular peaks in a moment, but let's take a look up at the molecular ion. Think the molecular ion is the molecule itself with an electron knocked off it. And with an electron knocked off it, it's not going to affect its charge. So let's work out the relative molecular mass of the molecular ion. It's going to have 3 H's, which comes out to be 1. It's going to have 2 carbons, and the other isotopes of carbon are much more scarce than C12, so we'll assume that it's 12, so that'll give us 24. Sorry, that should have been 3 for the 3 hydrogens. That gives us a total of 27, plus the chlorine. Problem is we don't know whether the chlorine's 35 or 37. Now if it's 35, that's going to give us a total of 62, whereas if it's 37, it's going to give us a total of 64. So you see, the heaviest particle we get is indeed 64, and that's where we would have specifically on this particular chlorine here, the particular isotope that's present in the molecule vinyl chloride is Cl37. When it's the lighter isotope, and remember the lighter isotope is 3 times more common, the mass of the vinyl chloride molecule will be 62. And if you look at the heights of these peaks, I think you'll see, if we take the relative height of that, comes about there. And if we take twice that, and if we take 3 times that, you can indeed see from the size, the relative sizes of the 62 line and the 64 lines here, that the 62 peak is about 3 times the other, which reflects this percentage up at the top in simple mathematical terms. Any idea then yourself about what's causing these? That there's one there. Let me just get rid of everything I've done so we can see it clearly. What have we got here? So we have a peak at 27, 26, and it looks like 25 as well. How would we explain these? Well, I think the 27 is relatively straightforward. That looks like it's fragmented the molecule like that. And that bit there will either be 35 or 37. And this bit here, of course, 2 carbons, 24, and 3 hydrogens, 3 ones are 3, that'll come out to be 27. So that particular one is being produced by a fragment, which is CH2CH. What about the 26? Well, that would seem to be a fragment created by knocking both a chlorine and a hydrogen off, one of the hydrogens. I'm not sure about this. It looks probably like it's knocking a chlorine off and 2 of the hydrogens. So a 25 could be explained by a molecule left with 2 carbons and a hydrogen. But there may be some other possibilities that I haven't seen. Let's look at another one a bit like that, dichloromethane. So the dichloromethane molecule looks like this. And this gets a little bit more difficult simply because of the statistics. Put that back. So, you know, is this chlorine 35 or is it 37? It's more likely, of course, 3 times more likely to be 35. Is this one 35 or 37? Again, it's 3 times more likely to be 35. But we certainly could have both of them 37. Now let's see what this bit adds up to in terms of its relative molecular mass. 2 hydrogens 2 and a carbon 12. So we're going to have 14 plus what comes from the 2 chlorines. Now, you see the possibilities with 2 chlorines. Let's say we've got 2 of these, 2 35s, that's going to give us a 70. That's referring to the 2 chlorines here and here. If we get 2 37s, that's going to give us 74. And we can also get a 35 plus a 37. And we can have, statistically it is different, 37 plus a 35. Now both of these give rise to a mass of 72. So at least I've shown you, hopefully here, what's causing each of these. Remember, we're adding these numbers to this 14 up here. So that would come out as a 70 plus a 14 is 84. This would come out as a 74 plus a 14 is 88. And this would come out as 74 plus a 14, the 14 being the CH2 part, and that would come out obviously as 86. So the 86 is being caused there by having the one Cl35 and one Cl37 on it. Why, given that there's twice the chance of getting this compared to the other possibilities, why isn't this the biggest peak? The reason is you've got to take in also the fact that the lighter isotope Cl35 is 3 times more abundant. So it doesn't surprise me that this 84 does come out to be a taller peak. But you'd have to be good at statistics and do lots of accurate measurements there to make clearer sense. But we've got enough from that. We've been able to establish what's causing each of these peaks. And we have a rough idea as to why the peaks are different sizes. We'll just strip everything away and see if there's anything else we want to observe on this particular graph. This one here looks to me like it's been caused by this particular one, where it's got 2 H's on here and it's got a Cl on here, but one of the Cl's has been knocked off, and this is Cl35, which would give the 2 C's would be 24. The 2 C's, am I right? 24. I'm not really sure about this, but if we put the other chlorine on here, let's make it a 35. But a 35, giving a 35 could be a 35, and what we would need then a 14 along with that. So it looks as if you can have what's called rearrangement, not just fragmentation but rearrangement, and this is way beyond the scope of A level, and I'm getting into areas I don't fully understand myself here, but that's leading me to think in terms of a carbon which is 12 plus 2 hydrogens. The other 2 would come from H and H. So whether it fragments and then rearranges in some way, so that perhaps you had ended up, because of fragmentation and rearrangement, that kind of particle there, that would indeed have 12 and 2 is 14, and 35, giving a total of 49, which would explain that peak. If I replaced that with if I instead of having a 35, I had a 37 on there with a carbon and 2 hydrogens, that would explain the 51. As far as these tiny little peaks here are concerned, if they have a mass to charge ratio, and remember that's what this is here, mass to charge ratio, if they have a mass to charge ratio exactly half of some of these up here, then they have been caused by the same particle having not 1 but 2 electrons knocked off. So when you divide the mass not by 1 but by 2, it gives you a mass to charge ratio half that of another. So if you take there, for example, 84, if there was something around 42 there, or at 42, that would be the same species as this, but with 2 electrons knocked off. At least that's the strong likelihood there. What about the presence of 2+ ions? Let's have a look at this. If there were also 2+ ions present, you would know, because every one of the lines in the so-called stick diagram there that we've been looking at would have another line at exactly half its mass to charge ratio. And you see the symbol that's used for mass to charge, M for mass, and Z is used as a symbol for the charge, 1+, 2+, and so forth. Those lines would be much less tall, because the chances of forming an M2 or a 2+ ion are much lower, much lower than forming a 1+. In other words, knocking 2 electrons off. So the lines as a result would be less tall, because the chances of the chances being so much lower. Looking at fragmentation now, we've already been glimpsing at that. Carbon dioxide. I'm suggesting here what has caused these sticks in the stick diagram here. There's one here at 25, 26, 27, 28. And that can be accounted for. Carbon is 12 and an oxygen is 16. You can see they add up to give 28. And then if it had fragmented that way, the remaining oxygen is 16, and it's 15 there, so this one is indeed 16. And what's giving, had forgotten about this one, what's given the 44? Well, that's the molecular ion. That's the CO2 with an electron knocked off, so it's got a positive charge. That's the so-called M+ peak. Another example here, fragmentation. Here we've got, what have we got? We've got CH3, CH2, CH3. So the overall molecule is C3H8. We're dating here with propane. And I've just picked out some of the fragments. Obviously, the molecular ion with 3 carbons, 3 12s to 36, and a total of 8 hydrogens, 8 should give us a total of 44. So this is indeed the molecular ion here. This is 45, and we see this is one short of 45, 44. Now these fragments, a CH3 would give us 12 for the carbon, and 3 hydrogens gives us a total of 15, which is this particular peak here. A C2H5 is made up of 2 carbons, 2 12s are 24, and 5 hydrogens. 5 ones are 5, so you expect a peak at 29. And that's what this big peak is. There's a lot of ethyl groups showing up on the detector because of the relative tallness of this particular stick in the stick diagram. And these could be put down to the fact that hydrogens are getting knocked off, so that the mass is falling by 1 for each hydrogen that comes off, perhaps. Similarly here, once we get the ethyl with 29, maybe the ethyl begins to lose hydrogens as well, which would explain some of these. Looking now at chain structural isomers, and here suggesting looking at hexane. Hexane is C6. It's an alkane, so it has twice as many hydrogens plus 2. 2 6s are 12, 14. So 6 carbons in a row, straightforwardly. In terms of our bonds, they go in like that. The valency of carbon is 4, so we must have 4 bonds to each carbon. And there's a hydrogen at the end of each of those. Hexane shows the same fragmentation pattern as other unbranched alkanes. Thus you get alkyl carbocations. The 15 would be caused by a CH3, for example. 29, what would that be caused by? Presumably C2H. 24, C2H5 would be 29, and so on. 43, 57. So imagine getting fragments that are CH3, C2H5, and so on. No reason why you mightn't get that as a whole fragment, etc. Or there's an ethyl fragment being produced with 29. The mass to charge ratio equals 57. And it's explaining here 29 is the ethyl group and so forth. And it talks about the relative abundance of these. It just simply depends on what's most likely to which part of the molecule is most likely to fragment when struck by electrons. But then once branching takes place, so that instead of having a straight chain of 6 carbons, you have a shorter chain with more branching. It goes on to say chain branching clearly influences the fragmentation of this isomeric hexane. And if you put a hexane in and then a structural isomer of hexane, for example, let's pick a relatively simple one where we reduce it to a 4 carbon chain and stick a methyl group on, let's say, in those 2 positions. When you would get the graph from a computer printout of these separately, the printout would immediately show a striking difference between these 2 samples, because the kind of fragmentation you get for these samples would be quite different. I'm not going to go into the detail, but you can pause if you'd like to read more of that. Now, we're going to finish by taking a look at the so-called M+2 peak and M+4 peak. And this comes up with regard to the presence of chlorine and bromine isotopes within molecules. It's on your syllabus and you need to take this in fully. The molecular ion M plus and M, sorry, that should say M plus 1 and M plus 2, each contain, is that right? No, sorry, it was right in the original place. There's a so-called M plus ion, and then there's the M plus 2 ion. Each contain one chlorine atom, but the chlorine can be either of the two chlorine isotopes. It could be a Cl35 or it could be a Cl37. The molecular ion containing Cl35 isotope has a relative formula mass of 78, so that's just made up. It would be helpful here if this had come out. Some of this hasn't come out on this slide. Most importantly, the actual chemical hasn't come out, which is 2-chloropropane. So if you think of a 3-carbon chain here with a chlorine on the middle carbon, the rest are hydrogens. This is 2-chloropropane. It's made up of a total of 3 carbons, which 3 12s, 36. It's got 7 hydrogens, gives us 7. Now that part, excluding the chlorine at this stage, that comes out to give us a value of 43. Now the chlorine is going to add either 35 or 37 to that. So we're going, if it's 35, we're going to end up with 78. And if it has the 37 chlorine isotope, then it's going to come out at 80. 43 and 37, 80. Now again, unfortunately the numbers haven't come out on this grid here. This particular line here is 80, 70, and so on. Maybe you can count them back there. Where we've got this very tall line, it's 40 there just to the left of that. That's 50, 60, and so on. This would be 30 and 20. Now, this here, the so-called molecular ion, that's the one which you can see is the tallest. That's the most common molecular mass for the molecular ion itself. It's this molecule containing a Cl35 with an electron knocked off it, and that is your M plus ion. But there is a possibility, just a quarter of the possibility of this, that it could have been the one with Cl37 on it. And that would be 2 up from the molecular ion, the M plus ion, and that's referred to as the M plus 2. And the plus 2, the significance of that is the difference in the relative atomic masses of the two isotopes of chlorine. So in summary, this is the molecular ion. In the molecular ion you put the most common isotope, in this case Cl35. If you find its relative molecular mass, it turns out to be 78, and you find that peak on the graph, regardless of whether it's the last peak or not, it should be the taller of the final peaks on the graph, but it'll be the M plus, the so-called molecular ion peak. If you find that you get a smaller peak to the right of that, 2 units up, this should make you suspicious of the fact that we're dealing with chlorine isotopes, explained by the fact that the less common isotope has a mass 2 units greater. You can pause if you want to read a fuller explanation down here. I'm afraid again a lot of the information is missing on this page, so let's add this. This particular spectrum refers to 1,2-dichloroethane. So we're dealing with ethane where hydrogen has been replaced on both carbons by a chlorine. So here the C2H4 bit, the 2 carbons add up to 2 12s or 24. The 4 hydrogens add up to 4, so we have 28 from that. Now the complication is here with 2 chlorines, so we could be adding on 35 plus 35, we could be adding on 70. We could be adding on 35 plus 37, we could be adding on 72. Could be the other way around, 37 plus 35, which is also 72. or it could be 37 plus 37, which is 74. So we could have a number of different possibilities here. We could have 28 add on 70, would give us 98. We could have 28 plus 72 gives us 100. We could have 28 plus 72 gives us 102. And we could have 28 plus 74 if both chlorines are the heavier, less common isotope, and that would give us 104. Now, what's going to be the molecular ion, do you think? Well, again, the molecular ion will be based on the molecule that contains, in both cases, the more common isotope. So this is the molecular ion. On the basis that Cl35 is more common, we expect that to be a relatively tall peak. And we're getting it there. And that should correspond to the mass of that particular sample, which is the one with 70 and 28, 98. What's the significance of the M plus 2 and the M plus 4? Well, the M plus 2 is being caused by this one, well, either of these, which give 72 plus the 28, which comes out as exactly 100. So the M plus 2 is exactly on 100. It's called the M plus 2 peak. The M plus 4 peak is the one where both of these chlorines are 37s. That gives us 28 and 74, 104. And that's a relatively small peak, which you can just about see there. Again, if you like to pick up a little bit more detail, you can pause and read what's below here. This one, the sample this time, involves bromine. And it's important for you to appreciate that when it comes to isotopes of bromine, the isotopes are 79 and 81, you may see here. In terms of their relative abundance, they're almost equally abundant. The lighter isotope, 79, is about 50.5% abundant. And the other one then is 49.5% abundant. There's very little difference in them. Now, the molecular ion in this particular case is going to be the one which has the lighter, more common isotope, Br79. Now, if you add up the mass of the ethyl part of it, the ethyl part is 2 carbons, 2 12s are 24, and the 5 hydrogens give 5, so that comes out as 29, as I've said here. Now, you can add to that 29 either the 79, or to the 29 you can add the heavier isotope of 81. So you'll either get 108 or 110. Now, the 108, this particular one, which is the molecular ion with the lighter, more abundant isotope of bromine, that comes out as 108, which is why, again, these numbers unfortunately are missing. This is 110 here, and this is 100, and this is 90, and so on. So hopefully you can see that indeed that is the case. This particular one is coming out at 98. Then at M plus 2, sorry, that should be 108, of course. That's 108. And then this one at M plus 2, in other words at 110, represents the bromoethane molecule, where it has the heavier bromine isotope instead. Again, pause and read this if you wish. Make sure you understand the significance of the M plus for the molecular ion, and then if you have an M plus 2 or an M plus 4 peak. M plus 2 peak, these are associated with molecules that contain chlorine and bromine, where the isotopes, there is a marginal difference in the relative abundance of the isotopes of bromine, and not a very big difference. Even a difference of 3 to 1 is not a huge difference in respect of chlorine, and these do therefore give significant peaks both for the lighter and the heavier isotopes. And one needs to be aware then of the relevance of an M+2 and an M+4 peak. If we're getting M+2, that's arising from one atom of the heavier isotope, and if we're getting an M+4, that's arising from two atoms of the heavier isotope. What about O16? Well, we're not going to get anywhere with O16. O16 is normal oxygen. In isotopic labeling, instead of having O16, we use the much rarer O18, which is two additional neutrons, obviously. I should also read 18 here. It's used, for example, you should remember at least one example, and here's one relatively simple example. It's used in esterification to show where the H comes from and the OH comes from. When we react an ester, when we form an ester by the reaction of a carboxylic acid with an alcohol, it's the OH group of the alcohol that's involved there. Let's use, I've intentionally drawn the alcohol back to front. Now, we know that water is created as a result of the interaction of groups here, H2O. And it's produced because something gives up an OH and something gives up a H plus. Now, if one was to think in terms of acid-base chemistry, one would be inclined to think, well, it's probably the H coming off the acid, the carboxylic acid group, because that's what acids do. They give up hydrogen ions, what we call protons. So you'd probably be inclined to go like this. But as it turns out, you'd be wrong. And this can be proved because if you label the oxygen, for example, let's say you label the oxygen, you manage to make ethanol that has O18 in it instead, which I'm using the red asterisk to indicate here. If this had been correct, then where would that OH show up? Well, that OH should show up in the water. And the radioactivity associated with that oxygen should show up in the water and should not show up in the ester. Because according to what you've presented there, you should end up with ORC double bond O, the O being part of the ester, and then the alcohol, if I go turn to blue, has provided the CH2, CH3, if you're right. But it turns out, in fact, that if you label the oxygen as I've shown here, the oxygen in the ethanol, it turns out, in fact, that that is in the ester. And as a result, the mechanism is in fact like so. It's not in fact an acid-base type of reaction that explains the mechanism of this reaction. And that's what catches us out. The H comes off that, and the OH comes off the carboxylic acid. So in terms of the product, if I use two different colors to present the product, we've got the ORC double bond O coming from the carboxylic acid. The rest, the O and the CH2 and the CH3, comes from the alcohol. Normal carbon is C12. What about C14? C14 can be used as an isotopic label to determine mechanisms. And this is particularly the case in metabolic cycles like glycolysis and the Krebs cycle. If you manage to produce carbon dioxide, which is made up of C14 instead of C12, it helps you to trace through the different stages in the reaction where the carbon's going, and if it goes on to one molecule and you find it there, then perhaps you can trace how that molecule goes on to interact in a different stage of the same cycle. And it works because C14 is a beta emitter. So if you have a device that picks up beta emission, you'll be able to detect which particular sample it's showing up in. and running for just over an hour. That completes our study of, or our lecture on mass spectrometry. You should now consider going on to look at a snapcast dealing with past paper questions from SIA, and indeed a third one that looks at past paper questions from other boards, principally AQA and OCR. Thanks for listening.